In this short video, we're going to take a look at how to represent graphs using matrices. This will be a good lead-in to the second part of section 10.3, dealing with graph isomorphisms. The first matrix that we can use, and I do want to point out that I've totally skipped over adjacency lists from your textbook because I don't see a lot of use in them. They're not useful computationally. Obviously, there are some advantages to using a matrix, as we know a lot of different ways to do computations with matrices. So again, going back to adjacency matrices, essentially what we're going to do is create a matrix where every time we have an edge connecting a vertex to another vertex or to itself, we're going to put a 1 in the matrix. And if there's no edge present between the two vertices, then we'll put a 0. So for instance, I have A, B, C, and D. And typically you would not label these. I'm going to label them just so that we're very clear on why we would put a 1 or a 0. Notice A is not connected to itself. So I'm saying there's no loop from A to A. So I'm going to put a 0 in my 0, 1 matrix. So this is going to be a 0, 1 matrix unless you have a graph with multiple edges, in which case you would have to use the value to represent the multiplicity of how many edges connect the two vertices. So again, A is not connected to itself, but A is connected to B, and so I'm going to put a 1 here in my 0, 1 matrix. And then A is not connected to C, but A is connected to D, so I'm going to put a 1. And then for B, obviously B is connected to A. We've already shown that here in the first row. B is not connected to itself. B is connected to C. And B is connected to D. For C, C is not connected to A. It is connected to B. It is not connected to itself, but it is connected to D. And for D, D is connected to A, and to B, and to C, and to itself. So this would be our one adjacency matrix for this particular graph. Again, typically we would not have these labels. The only important thing on the labeling is that the labels should go in the same order. But again, if I said C, D, A, B, then obviously this would be a completely different matrix. So that's why I said there are n factorial different adjacency matrices, depending on the order in which you list the vertices as you are creating your matrix. The other type of matrix that you can create is called an incidence matrix. In an incident matrix, obviously we know the term incidence when we're dealing with graph theory says that an edge is incident with specific vertices. So essentially what I would have to do is I would have to label E1, E2, E3, E4, E5, E6. So my matrix would have the edges, the vertices and the edges. So this one I do have to have those labels, E2, E3, E4, E5, E6. So again, here I'm going to put an entry of 1 if the particular edge is incident with the vertex, and 0 if it's not. So for instance, for E1, E1 is incident to both A and B. So there would be a 1 for A, a 1 for B, and a 0 for the others. E2 is incident with B and C, so 0, 1, 1, 0. E3 is incident to C and D, so 0, 0, 1, 1. E4 is incident to only D, so 0, 0, 0, 1. E5 is incident to B and D, so 0, 1, 0, 1. E6 is A and D, so 1, 0, 0, 1. So again, the obvious drawback is that if you have a very complex graph, I would have to go through and label each of those edges In this case, we only had 6 edges, but for that reason, I actually prefer the other matrix. As promised, this was a nice short video. Up next will be a little bit longer because we're going to take a look at graph isomorphisms.